So I'd like to talk about how we do sort of spatial spreading, which sort of becomes the basic concept for how do you do simple spatial low-pass filtering. And this also sort of gives you a way to think about what happens when I have resistive networks, a whole range of resistive networks where, I might have different resistances to a fixed potential and conductances between those nodes. And this gets kind of interesting because we see these structures in modeling in a whole range of places, usually to model phenomenon that are really eventually sort of meant to be partial differential equations type of things. And so one thing you can do if you look at sort of a resistive sort of spreading network like this, say G connections horizontally, resistances to going to ground, is to say, well, let's go ahead and actually analyze it. And we're thinking about this as being a large network. So this is, position n plus 1, position n minus 1, and it just goes in both directions. Eventually you'd have to worry about what the boundary conditions are. Let's not get too deep into that question yet. And so then the question would be, okay, so if I look at this node here, which is V sub n, and I could actually write KCl at this node. I've got conductances, so I'll just use the two conductances directly. So basically I can say, basically do KCl at this node. I've got current in, current coming from two other places, so I add all those up. It's got to be equal to the current going down to ground. Okay, not so bad. So I write that equation, do a little bit of rearranging in the math, and you think, okay, I've got R times G, and I've got the Vn structure, and I've got this sort of interesting term here. Same sort of thing could be said in terms of what is the currents that are being dropped. And notice the current representation looks very similar. Why? After all, that the current at I0n is just basically related to that voltage N through R. So no surprise that there's going to be a linear relationship between them. What is interesting is that if I take a look at this structure and I have many, many nodes, I can then start to say, well, this looks like a partial differential, this looks like a differential equation, because I notice that I'm taking the value here, subtracting it, multiplied by 2, subtracting it from its neighbors. This is an approximation of the second order derivative. So it looks like I have a current coming into a second order spatial derivative here, and then there's some sort of loss term going through this. Well, I can look at both of these elements, both in voltage and in current, and actually end up writing and basically saying, well, if I take that approximation, thinking now R and G as sort of per unit length constructs, I actually get both of this is a differential equation in voltage and the same one in current. Where R times G I would talk about as the space constant. Actually, it's the space constant squared, which then allows me to look at this basic sort of structure. And I can utilize this in terms of spatial filtering. If I wanted to add capacitance and model that would be terms that would be added over here. And so you think that's kind of nice and interesting resistors, but if you now start to think about things like transistors, which you go, well, these are horribly nonlinear elements. I don't know if I would ever see anything similar. Well, let's just kind of see. And one of the things I get is I can take a look at a whole transistor block. You sort of see this sort of structure in here kind of feels like a very simple diffuser network. And in fact, what you get is a combination of diffuser elements, if you're familiar with that. The diffuser concept comes from Kwabena-Bowen's original sort of work, and many different people connected to it. Some people call them pseudoresistors. That's a related sort of connection and phrasing to it. But the thing is you start off with that your currents here, I0n, much like we had with this resistor related I0n to V sub n. Here, I0n is related exponentially through some sort of weighting value, which is now going to sort of be all the prefactor elements for V. That's going to be a kappa V1 and all the other terms in that system. Okay. And then I can look at currents maybe between here. And I would say, they actually have maybe some ratio of weighting. So maybe W2, which is related to the V2 term. But now it's still linear in these terms. And so you can start to write linear expressions, and what's interesting is the W2 over W1 and all of these terms here looks incredibly similar to this expression, except that instead of its RG, it's now W1 over W2. W1 over W2 is going to be related to e to a kappa V2 minus V1 over UT, because you're going to be seeing that with your subthreshold elements. But otherwise, this looks the same. And I can make the same approximation in making a differential equation out of it, where now my space constant, lambda squared, is related to this ratio, which is quite tunable. So it's not only that this is linear, at least in current, and in current these numbers look identical. In voltage would be different. In voltage it is, well, what? It is a sort of log compressed version. And that could be useful if you're doing things over wide dynamic range, but it's something you've got to know what you're dealing with no matter what you work with, but it's there. And it's a tunable sort of space constant, which could be very useful for a range of applications. So although it looks like a very interesting sort of simple resistive network, what you realize is that this is quite implementable in CMOS structures, and not just implementable, but quite tunable and efficient in those spaces.